Our model at this level has led us to the following conclusion. Starting with the coin facing upwards, tossed with a translational speed v and an angular velocity omega, it is caught at some termination time tau when the coin returns to its starting position with some angle theta of tau that it makes with the horizontal. A student will recall from her high school physics classes that the motion of such an object is completely described by Newton's laws of motion. If the listener has not seen these before, she might perhaps be willing to take these on faith. These are going to be very simple equations which completely characterize the motion of this coin. If for no other reason than to see how the story turns out. But in any case, let's begin by considering the height the coin is at time t. Now, the coin, starting at height 0, is subjected solely to a gravitational force pulling it down back towards the surface of the Earth. There's an initial velocity v pointing straight upwards imparted to the coin, and the student might remember the following famous formula. The height the coin will be at time t is given by the equation vt minus 1/2 of gt squared. The quantity g, of course, the student will recall, represents standard gravity, the standard acceleration in free fall at the surface of the Earth. The standard value for g is approximately 9.8 meters per second squared. In any case, now here is a completely simple algebraic representation of the height of the coin at any given time t. We should very quickly check to see whether the initial conditions are satisfied. Well, at time 0, on the right-hand side, I get 0, and therefore the height of the coin at time 0 is, as prescribed, 0. Well, what about the height of the coin when it actually returns to its starting point? Well, this, we recall, is the termination time tau. Plugging in t equal to tau into our equation, we see that the height at time tau, y of tau, is given by v times tau minus 1/2 of g tau squared. But we are considering terminating the experiment at the same height at which we launched the coin, and therefore y of tau is compelled to be 0. But this gives us now a very simple equation that we can solve for the parameter tau. Tau, the termination time, is now completely determined by the initial velocity v and the gravitational acceleration. Tau is exactly twice v over j. So, if I know ahead of time what the velocity is going to be, I can tell you when the experiment will be terminated. The coin will return at time 2v over j. Now, what about the angle it makes? Well, recall that the angular velocity is constant at some omega, so it's spinning around the horizontal at a certain speed. Now, when you have a constant spin, then the angle that is covered is proportional to time, and therefore the angle theta of t at time t that the coin makes is exactly omega times t. A quick sanity check: at time 0, its initial angle is in fact exactly 0. But now here we come to the rub. At time tau, where the coin returns to the hand, the angle it makes, theta of tau, is of course omega tau. But we know what tau is. It's 2v over j. And therefore we come to the conclusion that the angle that the coin makes with the horizontal at the moment that it is captured is 2 omega v over j. A beautiful, elegant equation, glorious in its simplicity. And in this simple equation, it carries a tale.